All righty. I guess today we'll talk about alternative coordinates for triple integrals. So two ideas we'll talk about are cylindrical coordinates and spherical coordinates. And we've kind of been doing cylindrical coordinates already. Essentially, anytime your xy shadow d is appropriate for polar coordinates, that means that the triple integral is probably going to be appropriate for cylindrical coordinates. So if you remember, whenever we're doing the triple integrals, if you're putting dz on the inside, the first step is to figure out your bottom and top surfaces. So z equals g1 of xy to z equals g2 of xy is your bottom and top surfaces. And then this xy bounds on the outside, that's going to be from your region D, which is the shadow of your solid region E in the xy plane. And so if D is good in polar, then you might want to think about converting the triple integral to what we'll call cylindrical. So anyway, yeah, the idea of cylindrical, you're literally just converting x and y into polar. So x becomes r cosine theta, y becomes r sine theta. And therefore we have these other relationships. And so I guess you want to think about r as being the distance from your point xy to 0, 0 when you're in the xy plane. So for polar coordinates, r is the distance to the origin. But in cylindrical coordinates, you're going to want to think of r as being the distance to the z-axis. So, and for cylindrical, r is the distance between x, y, z and the z-axis. So that's how we're viewing that picture here, that this distance here is r. Okay. And so let's take a look at converting some points. So what are the rectangular coordinates for the point with cylindrical coordinates? 2, 2 pi over 3, 1. So these are r, theta, and z. So, okay, well, z is 1, right? Because with cylindrical coordinates, you're just leaving z alone. You're not doing anything to z. And so x is r cosine theta, so 2 cosine of 2 pi over 3. 2 pi over 3 is this angle here. So its reference angle, I guess, is pi over 3. It's second quadrant, all that fun stuff. Your cosine of 2 pi over 3 is minus 1/2, so you end up getting minus 1 as x, and then y is r sine theta, so 2 sine of 2 pi over 3, which is 2 times square root of 3 over 2. Your reference angle is, again, pi over 3, but sine is positive in the second quadrant, so you end up getting square root of 3. So going from cylindrical to Cartesian, you just use x is r cosine theta, y is r sine theta, z is z. As far as figuring out cylindrical from Cartesian, again, nothing happens to z. So z is minus 7 in our cylindrical coordinate system. And then this point 3 minus 3, we basically just need to convert to polar in the xy plane. So r is the distance to the origin, which is the square root of x squared plus y squared. So you end up getting, be careful, 3 root 2. So you'll have the square root of 18. And so you end up getting that. And then theta is, well, it's up to you. You could call theta 7 pi over 4 or minus pi over 4, whichever is more convenient for if you're doing other stuff with this region. But yeah, again, remember there's infinitely many different theta values for any given point, but the first two that come to mind for this would be minus pi over 4. So thinking about your special angle there. Okay, so again, the big hint for cylindrical coordinates are whenever your shadow D is good in polar, and that also happens a lot in the case where your solid region E has symmetry around the z-axis. So if you have symmetry around the z-axis, then the shadow tends to be a disk of some sort or maybe an annulus, but either way, If your solid has that type of symmetry, your shadow D is going to be good in polar. So we could just think, okay, well, what's the surface with equation R equals C? So it's the set of points R away from the Z-axis. So remember, in cylindrical, you want to think of R as being distance to Z-axis. So it's all points that are R away from the Z-axis, so you get infinitely tall cylinder. I guess the other way you could do it is just mess around with the equation, right? R is the square root of x squared plus y squared. So x squared plus y squared equals c squared is this thing. And so remember, we learned about cylinder equations way back in chapter 12. But yeah, we get a cylinder. I guess I should say it's a circular cylinder around the z-axis with radius c. I guess I should make this a c. Okay, and then what is the surface with equation c equals r? So one way you could think about it, if you have like a surface z in terms of r, draw it in the rz half plane when r is positive, and then you just kind of spin it around the z-axis to generate the 3D surface. And so if you spin that line around the z-axis, you're going to get a cone. I guess it's technically a half cone because if you play around with this equation, you'll see that z is, well, what is r? R is the square root of x squared plus y squared, which is the top half of z squared equals x squared plus y squared. So remember back in chapter 12 when we were doing quadratic surfaces, we would have probably written that z squared equals x squared plus y squared, and that has both pieces of your cone. But if I solve for z and take the positive square root, I only get the top half where z is greater than or equal to 0. So you could call that a half cone or something like that. Okay, so anyway, I guess we could talk about converting the triple integral. So essentially, the first step is the same. That cylindrical, you're still thinking bottom and top surfaces, z in terms of x and y. And then the only thing you're doing differently is you're setting up the dy dx bounds as dr d theta, which then also has this extra r. So essentially, I'll show you what we were doing last week on the next slide. But we're literally just converting the x and y bounds into polar. The only other thing that has to happen is that x and y have to be changed to r cosine theta and r sine theta, just like we did in polar. And that has to happen everywhere. So any x's and y's that you might have in your z bounds also need to be converted into r cosine theta and r sine theta, respectively. So anyway, let's just take a look at an example, and you'll see that it's really not much different from what we were doing last week. So a solid lies within a cylinder, below a plane, and above a paraboloid. The density at any point is proportional to its distance from the axis of the cylinder. Find the mass of E. Okay, so density, it says, is proportional to the distance to the z-axis. That's the axis of this cylinder. And so that is square root x squared plus y squared. So yeah, our density function is going to be some constant of proportionality times this. And so what we did, so last week's method, what we would have done for this is we would have said, okay, let's figure out my bottom and top surfaces. It sounds like the bottom surface is z equals 1 minus x squared minus y squared. So our bottom surface would correspond to our bottom lower bound for z. And then our top surface is the plane z equals 4. So that's our upper bound for z. I have my integrand, which is the density function. And then I have my dz. And then the way I showed you last week, I said, you know what, because we're eventually going to switch the xy bounds into polar coordinates, we might as well not spend the time and write out what they are in terms of y goes from the bottom half of the circle to the top half of the circle. You could just leave it, your xy bounds, as this disk. And then The first step is you do the z anti-partial derivative. So you'd have, x squared plus y squared less than or equal to 1. And then your z antiderivative would give you 3 plus x squared plus y squared times k square root x squared plus y squared dA. And at that stage, then you would switch into polar coordinates, so 0 to 1, 0 to 2 pi, 3 plus r squared k r d theta dr. So you made your conversion there. So last week we sort of faked cylindrical coordinates by first doing the dz integration on the inside. And once that was taken care of, we got a double integral, which then we were able to just convert to polar like we did a few weeks ago. So essentially, what we'll do today, now that we know cylindrical coordinates, is it allows you to do that conversion when you still have the triple integral. So honestly, it's not 100% necessary to even really talk about cylindrical coordinates, but the reason we do is because there's going to be something quite different called spherical. And so understanding the differences and the similarities is really going to be instructive. If we were only ever going to do cylindrical coordinates, we probably wouldn't even do it. We would just do what we did last week, where after you do the inner step, you just switch to polar once you have the double integral. But trust me, it is going to be useful to think about cylindrical coordinates and compare and contrast to the idea of spherical coordinates. So anyway, how would we do this with cylindrical? Well, I guess I can write my density in terms of r, theta, and z. So k times square root x squared plus y squared becomes kr. And then the bottom and top surfaces, they have to be changed x and y into polar. So nothing really happens on z equals 4, right? Because there's no x's and y's. But if I redo the bottom surface, z equals 1 minus x squared minus y squared, if I convert x and y to polar, I get z is 1 minus r squared. So the way this is going to look in cylindrical coordinates is my integrand is kr. So I didn't really spell it out, but the extra r that we have in polar, basically we have it in cylindrical. So dv is r dz dr d theta in cylindrical. And the order doesn't matter if your bounds are all numbers. I guess typically our bounds for r and theta are going to be all numbers. Our z bounds are going to contain r, so standard, you'd probably have z on the inside. But if you end up having all numbers, then the order doesn't matter at all. But the typical situation is that, yeah, your z bounds will contain r and or theta, which means z has to be on the inside. But anyway, yeah, because that's what happens here. Our bottom surface is z equals 1 minus r squared. Our top surface is z equals 4. So yeah, your z bounds have r, therefore z has to be inside of r. But where theta and r are relative to each other isn't really important. So anyway, that's the conversion to cylindrical coordinates for the triple integral. And you'll notice that you end up getting exactly what we had before. So essentially, the first step would be anti-differentiate with respect to z. So you'd have kr squared z between z equals 1 minus r squared and z equals 4 d theta dr. And so you'd have 0, 1, 0, 2 pi. When you plug in and subtract, you'll have kr squared times 3 plus r squared d theta dr, which if you rewind back, that's what we got a few minutes ago when we waited to do the polar conversion on the double integral. So that's the idea of cylindrical. Really, nothing's happening to z. You're still thinking bottom and top z surfaces, but your x and y, everything gets converted to r and theta. So let's do one more example of cylindrical coordinates. So you'll get a lot of practice, but looking at these x and y bounds, thinking about visually what's going on, the shadow, these x and y bounds are describing us a disk of radius 2, right? So y equals plus square root of 4 minus x squared, y equals minus square root of 4 minus x squared. Those are just the top and bottom halves, respectively, of that circle of radius 2. Okay, and then trying to visualize what's going on here, z equals square root x squared plus y squared. That's a cone, and that's our bottom surface, right? Because it's our lower bound for z. And then the plane z equals 2 is the top surface. So our solid region is that blue solid cone pictured. Okay, and so let's convert this to cylindrical. So really, that we're just converting x and y into polar. So this is a disk of radius 2. So our r and theta bounds are 0 to 2, 0 to 2 pi. My z bounds, I just convert x and y into polar. So what is square root x squared plus y squared? That's r. What is 2? Well, it's 2. What is x squared plus y squared? Our integrand is r squared. And then dz, dy, dx becomes r dz, d theta, dr. So anytime you're looking at things like square root x squared plus y squared, or square root 4 minus x squared, the anti-differentiation is probably going to involve some kind of trig substitution. So we don't want to have to worry about that. And so anytime you see both something like this, that's shouting at you that you're dealing with some kind of disk as far as the xy shadow goes. And then anytime you see x squared plus y squared, either like that or in a square root, that's a hint for cylindrical / polar coordinates. They're pretty much the same idea. And so, like I said, the real insight you're going to gain from thinking about cylindrical coordinates is going to be from comparing and contrasting it to the idea of spherical coordinates. So let's get into that. So I bet at this point, if I were to ask you a question, which coordinate system, cylindrical or spherical, is more similar to polar? I know we haven't talked about spherical yet, but you saw that for cylindrical, you literally were just keeping z by itself and changing x and y to polar. So in some sense, you're probably thinking, I don't know what spherical is yet, but there's no way it's more similar to polar than cylindrical is, because cylindrical pretty much seems like polar. You know, I did the same exact equations as I did for polar. So equation-wise, I'd say that's true. Cylindrical is more similar to polar. But concept-wise, I think spherical is actually closer. And so here's why. So what I want to do right now is to just really think about these 3 different coordinate systems as far as what they're doing and what's special and things like that. So for polar, of course, that's something we did for the xy plane. And the picture was something like that we had r was the distance to the origin, and theta was the counterclockwise angle from the positive x-axis. And so what's the deal with polar? There's a special point, the origin, and r is the square root of x squared plus y squared, is the distance from xy to that special point. So that's the situation with polar. Okay, so what's going on with cylindrical coordinates? We have r, theta, z. And so the picture we had a few slides ago was the following. So here's our point x, y, z. We have this here, r. And then we had the point down here, x, y, 0. We had this point here, which is x, 0, 0. And theta is the angle there. And of course, z is just z. But anyway, if you want to think about cylindrical coordinates, we don't really have a special point anymore. It's instead a special axis. So there's a special axis, which is the z-axis. And r is the square root of x squared plus y squared. So in R3, that doesn't represent distance to a point. It represents distance to the z-axis. So this is the distance from x, y, z to the z-axis. So the equations stay the same, but the concept of cylindrical, actually, when you think about it, is a little bit different from polar. We don't have a special point, we have a special axis, and this variable r denotes the distance to the special axis. Okay. Well, what's going on with spherical coordinates? So spherical coordinates are rho, theta, and phi. And so it's the same Greek letter we used for density last week, I suppose. But for some reason, I guess that comes historically from gas dynamics, fluid mechanics studies. But for some reason, in this context, rho corresponds to a distance. I don't think physicists use this notation. I don't know about engineers, but whatever. Just get used to it. We're using rho, which, okay, it's like a curly P. I guess I should say I got practice writing rhos a lot because I studied gas dynamics, and you have two quantities, density, rho, and pressure, P. And any of you engineers in aerospace, if you have to take a fluid mechanics class, you'll get practice telling your P's apart from your rhos because some genius decided to have both of those in the same equations all the time. But anyway, we're not talking about density anymore. Rho is going to be a distance, and then we have two angles, theta and phi. And so we'll talk more about these angles in a second, but let's just draw the standard picture here. So if this is x, y, z, so what's going on with spherical coordinates? There's a special point which again is now the origin, but we're in R3, so 0, 0, 0. And rho is going to be the distance from x, y, z to the origin. So spiritually, I think, well, in that sense, spherical is the natural extension of polar. Like equations-wise, you're recycling equations for cylindrical and polar, but the concept of having a special point and being the distance from XYZ to that special point, that concept is extended into spherical. So now you see the subtle differences. You thought that you couldn't get more similar to polar than cylindrical. Maybe qualitatively, maybe spiritually, spherical is closer. Because it's distance to a special point, the origin. Okay, and so let's start talking about what the other spherical coordinates are, the two angles, theta and phi. And so understanding that, it's going to amount to understanding these two triangles. So any point we have x, y, z, we can draw one triangle that contains 0, 0, z and 0, 0, 0. The other triangle that we can have contains 0, 0, 0, x, 0, 0, and x, y, 0. So I guess that one's written out. I don't have to do that. But let's draw these over here. So my one triangle is, 0, 0, z, 0, 0, 0, x, y, z. And then our other triangle is 0, 0, 0, x, 0, 0, x, y, 0. Okay, and so theta, you might notice, it's the same theta that we had in cylindrical coordinates. So we're not going to be mean and use the same letter for something different. It's the same theta you're used to. So counterclockwise angle from the positive x-axis, that's your angle theta. And let's start drawing some other things in. So basically this leg is x, this leg is y, this leg is z. R is not a spherical coordinate, but it can be a handy intermediate step. So let's realize that, the hypotenuse of that triangle is R. It's the distance from XYZ to the z-axis or the point xy0 to the origin. So anyway, r goes there, and then r goes up here, and this here, the distance from 0, 0, 0 to xyz, that's our distance rho. Okay. So what we want to do is find the relationships of different things. Let me just see. Okay. Okay. So what are all the important equations here? So anyway, I guess we know that r is the square root of x squared plus y squared. So anyway, oh, and sorry, I didn't mention what phi is. Phi is this angle here that appears in this triangle. So phi is, in some sense, the angle down from the z-axis. And so now to figure out the equations for x, y, and z in terms of rho, theta, and phi, it's just a matter of doing right triangle trigonometry. So equations that we're going to want are the fact that z is the adjacent side in this top triangle, so that means that z is equal to rho cosine phi. And then also in this top triangle, well, I guess the bottom triangle tells us that x and y are r cosine theta and r sine theta. But the other thing this top triangle tells us is that r is the opposite side of phi. So r is actually rho sine phi, which means that you could substitute in for r to get that x is rho cosine theta sine phi. I'm just reordering the factors, no big deal. And y is then rho sine theta sine phi. So you're going to probably want to memorize these, but I'm just trying to show you here that if you remember back to right triangle trig from however many years ago when you learned that, you can actually figure out all these equations without having them memorized, but hopefully you do practice this stuff enough to memorize it. So what else do we have? We have that rho is the square root of x squared plus y squared plus z squared. And so just like we did in this class with polar and cylindrical, I know in Math 141 you drew pictures of roses where you let r be negative and do some silly pictures like that. But in this class we're thinking of r and rho as distances. So distances are never negative. So rho is never a negative number. We do that. So something else we're going to do, and I'll explain why later, is we're going to enforce that phi is always between 0 and pi. So with polar coordinates, remember, you usually think about theta as 0 to 2 pi, but sometimes you might relax that. So for example, if you wanted to do like the right half of a disk, you would let theta go from minus pi over 2 to pi over 2. So in certain situations, you might let theta go outside of that range when you're dealing with polar. And that's going to be the same thing here for theta in spherical. But there's something quite different about phi, in that phi we're always going to keep between 0 and pi, no matter what. There's two reasons for that. I'll get into that in a few minutes. But just as soon as possible, in your mind, think of phi as always being between 0 and pi, never anything else. So I guess the nice thing that that does is that keeps this equation for r positive. So remember, we wanted r to never be negative. If you think about the behavior of sine phi for phi between 0 and pi, sine phi is going to be positive. So anyway, that's good. What else is important to know? So I think I'll show you guys tomorrow where these calculations are coming from. It's going to be an optional topic that we won't quiz you on or test you on, but it turns out that dv for spherical coordinates is going to be rho squared sine phi d phi d theta d rho. So I'll show you tomorrow that optional topic as to why that's the case. But if you're not interested in knowing the why, what you got to do is just make sure you convince yourself that, yeah, this is what it's supposed to be. So anyway, this is our box of equations you absolutely have to know for spherical coordinates. commit those to memory as soon as possible. So it can be handy to think about what different variables equal to a constant are. So in cylindrical, if r is a number, you get a cylinder around the z-axis. If z is a number, you get a horizontal plane. If theta is a number, you get a half plane touching the z-axis. So that's essentially what happens here. That if you think about the surface, rho equals some number c, assuming c is bigger than 0, you get a sphere with that radius centered at the origin. If theta is a number, we're thinking of points such that theta, this angle here is the same. So if you were to adjust your perspective and look at this down into the xy plane, it would look like a half line that goes on forever, but in R3, that would be a half plane. And then finally, phi equals c. Remember, phi is our angle down from the positive z-axis, so phi is 0, is straight up. Phi is like pi over 4 is here. So once I've gone down pi over 4, once this angle here from vertical is pi over 4, that's that. If I do like phi equals pi over 2, that's actually the xy plane. This cone, you can imagine a movie where it's like opening up and then opens all the way up into a flat plane and then kind of keeps going and turns into a cone again. But anyway, that's just something to think about. So spherical coordinate conversion, what are the rectangular coordinates for the point with this? So x is rho cosine theta sine phi. So 2 cosine theta sine phi. Well, cosine of pi over 4 is root 2 over 2. Sine of pi over 3 is root 3 over 2. So what is this? Root 6 over 2. Whatever that is, who cares? Just some number. Y is rho sine theta sine phi. So 2 sine pi over 4 sine pi over 3. So 2, well, sine of pi over 4 is also root 2 over 2. So you get the same exact thing. And then z is rho cosine phi. So 2 cosine of pi over 3. Well, cosine of pi over 3 is a half, so you end up getting 1. So converting spherical into rectangular, you literally just use those equations. So what are the spherical coordinates for this point? Well, I know that rho is the square root of x squared plus y squared plus z squared, which is square root of 12 plus 4, which is square root of 16, which is 4. So what else do I know? I know as far as the angles go that tan of theta is y over x, and cosine of phi is z over rho. So it's the same theta equation we had for polar, we had for cylindrical, and then if you rearrange the fact that z is rho cosine phi, you see that cosine phi is z over rho. So tan theta is y over x. Well, it's actually undefined, but if we think about our xy shadow, we have 0, 2 root 3, 0, if I'm in the xy plane, I know that that angle is pi over 2. So tan theta, as you approach that, is plus infinity, so pi over 2, whatever you want to say it. Yeah, so this is sort of an edge case, but clearly our point, our shadow in the xy plane lives on the positive y-axis, which means theta is pi over 2. Okay, and then cosine of phi is z over rho. So z is negative 2, rho is 4. So it looks like cosine phi is minus 1/2, which means then that phi is inverse cosine of minus 1/2, which is 2 pi over 3. So again, there are going to be lots of other solutions, but no matter what, we keep phi between 0 and pi. We never break that rule. And 0 to pi, you should remember, is the range of inverse cosine. So that's nice, that you don't have to do any thinking as far as, it turns out, yeah, I guess I can write that here, that because of this, phi is always inverse cosine of z over rho. You don't have to worry about any other possibilities. Okay. So we have a lot of stuff here, and there's going to be a couple of things that I think that you guys might be a little bit suspicious of. So let's warm up with a problem whose answer we already know. So a ball, remember, is a fancy way of saying a solid sphere. That, if you want to go back to thinking about the SATs, a circle is to a disk as a sphere is to a ball. That a circle would be the points exactly the radius away from a point, whereas a disk is at most that distance from a point. Whereas a sphere is sort of a surface. It's like the Earth's crust. It doesn't consist of points on the inside, but a ball is a solid sphere. So it consists of all the points on the sphere or inside. So solid region. Whereas the surface, the sphere itself, is just the two-dimensional surface. So anyway, let's use spherical coordinates to calculate volume of a ball. Okay. So volume, if I want to use a triple integral, remember that's when I do a boring constant integrand f equals 1. So I need to do the triple integral of just plain old dv, and that should give me the volume of the ball. So I'm going to set this triple integral up in spherical coordinates. And so a few slides ago, I told you that dv has a factor of rho squared sine phi. So tomorrow I'll show you why, but today I'm going to convince you that it has to be there, because otherwise we're going to get not the answer we're expecting. So dv, always for spherical, is rho squared sine phi times your d phi, d theta, d rho. Okay, and so I guess the question then is, we need to give spherical bounds for this solid ball. And so remember, rho was never negative. So this ball basically consists of points between 0 and r away from the origin. So our rho bounds are going to be 0 to the radius, which is the square root of r squared, which is capital R. Just think of capital R as a number, whatever. Okay, and then what are our theta and phi bounds? So here I would say then that basically theta and phi should be everything. That when I have this ball, there's no restriction on the angle that I'm talking about. But so back when we did polar coordinates, we had to be careful to only describe each point once. That's why we never set up something like 0 to 4 pi or 0 to 8 pi, because that would go through each point twice or 4 times respectively, or 0 to 6 pi would trace out everything 3 times. So, okay, how are we going to make sure to do that in this case here? So I claim that what we're going to want to do is let theta go from 0 to 2 pi and phi go from 0 to pi. So I know a lot of you, anytime I teach this in person, I say, okay, what should our bounds be? A lot of people raise their hand and think it's 0 to 2 pi, 0 to 2 pi. But I claim that that's actually no good. So 0 to 2 pi, 0 to pi, I claim that that's what we want. So let's do it and make sure we get the correct answer. So I don't know if I didn't really talk about it last week in the when we learned about triple integrals, mainly because most of the interesting triple integrals we didn't have bounds all numbers. But back when we did double integrals, if your integrand is separable, as in can be factored, and your bounds are all numbers, then you are allowed to split things up. So for triple integrals, if I had something like a to b, c to d, r to s, times f of x, g of y, h of z, dz, dy, dx, then I'm allowed to do something like a to b, f of x, dx, times c to d, h of, sorry, that would be g of y, dy, times r to s of h of z, dz. So basically, to do this, make sure your bounds are all numbers, because if you have variables anywhere, this is total nonsense. Remember, number one rule is that the answer has to be a number. So if you have variables in any of your bounds, then you're going to run into trouble. But then also just be careful when you're doing these factorings. I see a lot of really sloppy stuff sometimes. If it's something like xy squared plus z, you can't factor that in terms of something of x times something of y times something of z, because you have this plus. So just don't do any silly algebra. But the reason I bring this up is because a lot of our spherical regions that we obtain do in fact have this nice property that the bounds are all numbers and the integrand is separable. So what I'm able to do here is do my, so I know capital R seems like it's a variable, but for the purposes of this, it's the known radius of the ball that we're talking about. So anyway, I could do this shortcut. And then, okay, let's keep going. My rho antiderivative is rho cubed over 3. When I plug in 0 and capital R, I get, don't divide by 0, big R cubed over 3. Integral 0 to 2 pi of d theta is just going to be 2 pi, right? Because our antiderivative of 1 is theta. And then 0 to pi of minus cosine phi, my antiderivative is minus sine phi. No, I'm sorry, it's sine phi. I got ahead of myself. Sorry, this was supposed to be a sine, which means that this is supposed to be minus cosine. And be careful between, so minus cosine of pi is minus minus 1, so 1, minus negative cosine of 0 is 1 plus 1 is 2. So anyway, when you do this out, you get 4/3 pi radius cubed, which, familiar? Hopefully. So let's convince ourselves that everything here is good. So as you can see, this is the good familiar formula that you learned, I don't know, a long time ago. What's the volume of a sphere? You called it. But I would say now more precisely, we should say it's the volume enclosed by a sphere or the volume of a ball. But whatever, 4/3 pi radius cubed. So let's see what goes wrong with some other things here. So first of all, importance of dv is rho squared sine phi, d phi, d theta, d rho. If you think, hey, yeah, I don't feel like I should have to include that scary looking rho squared sine phi. So if I set up the triple integral of just d phi, d theta, d rho, then essentially I'm just going to end up getting 2 pi squared as the radius times the radius, which is obviously not the correct answer. So the importance of this rho squared sine phi, it has to be there, otherwise you don't get this expected answer that you've known for years. 2 pi squared r is not the volume of a sphere. So importance of that. So I guess the other thing is What if I did 0 to r, 0 to 2 pi, 0 to 2 pi, rho squared sine phi, d phi, d theta, d rho. So those of you who thought, okay, well, to do all angles, let's let both of them go 0 to 2 pi, 0 to 2 pi. You'll end up getting the same thing for your r and theta integration. But when you do the antiderivative of sine phi, you get minus cosine phi. If I do that between 0 and 2 pi, cosine phi is 2 pi periodic, so that actually cancels out and you get 0. So it's like, what? The volume of this sphere is 0? I don't think that's right. And so essentially what happens here is that restricting phi to be between 0 and 2 pi, sorry, between 0 and pi, which is what we do. We never let phi go outside of 0 to pi. It keeps sine phi greater than or equal to 0. And this is important. Well, I guess it doesn't just keep that greater than 0. It keeps the rho squared sine phi, because again, we also restrict, well, I guess rho squared is never negative, so because it's squared. It's important that the factor on dv is greater than or equal to 0. Otherwise, you could get negative volumes. And so negative volume, I guess sometimes you might think negative volume is okay if it's below the axis, but that's when you're doing a double integral and calculating signed volume. For something like this, where we're doing the triple integral of dv, we don't want that to ever be negative, otherwise we could get silly things happening. Like this is just the volume of our region, no matter where that volume is. We never want it to be negative in this context. Otherwise, volume, not volume under a surface and above the xy plane where you let stuff below count negative. This formula here is just good old regular volume, no sense of signed volume. It doesn't care where solid region E is. The triple integral dv, you want to be the good old positive notion of volume. So anyway, you see then that you also would get the, so I guess technically what we'll talk about tomorrow is that there's going to be some formula and you have this absolute value of something called the Jacobian determinant, I suppose. You know, the Jacobian would be the actual array of partial derivatives. The Jacobian determinant would be the absolute value of the determinant of that array. So anyway, you might think, okay, well, fine, let's, and this is why back when we did polar, we never let r be negative because we were lazy. We don't want to have to do absolute value of r times d theta dr. We just want to do r d theta dr. So that's why we never let r be negative with polar coordinates. I guess you could say, okay, fine, I'll slap a absolute value on this sine phi. But if you go through the calculations, you'll get 8/3 pi radius cubed, which is also wrong. So I know some of you might still be skeptical, but hopefully this calculation that you all should be really familiar with, the formula 4/3 pi radius cubed, goes to show you little things like the 0 to pi is important, the rho squared sine phi is important. Messing around with any of those little details gives you things that don't make sense. So what's really going on with, what's really happening with if I let both theta and phi go 0 to 2 pi? So we saw funny business happens when you try to calculate this, but like what's really going on when this happens? Basically, you're double counting every point. So let's say that I'm dealing with let's say that this is my x-axis So my y-axis is going into the page and my z-axis is here. So let's say I have this point. Let's say it's, I don't know, let's keep it on the unit sphere. So we could do root 2 over 2. And, oh God, this is annoying. Well, whatever, let's just keep it simple. Let's not do this point. Yeah, let's do root 2 over 2, root 2 over 2, 0 is our point. And so I claim that I could get there by taking rho equals 1, theta equals 0, phi equals pi over 2. I claim I could also get there by doing rho equals 1, theta equals pi, and phi equals 3 pi over 2. So if I, yeah, maybe I'll move this stuff over here. Undo. I guess I don't need this arrow anymore. Whoops, that should be black. Okay, so to get there at theta equals 0, I'm swinging in the plane theta equals 0, which is the positive x-axis, and I'm stopping phi once phi hits pi over 2. Whereas if I do theta equals pi, I'm swinging down this way, and I'm going past the negative z-axis. Because again, like our angle, as far as theta is concerned, our angle theta is this angle here. So swinging at theta equals 0 means you're doing this. Swinging the other way, you're going towards the negative x-axis, which means you're going all the way around to get to the same point. So that's my claim, that these two triples of spherical coordinates give you the same thing. And you could confirm that by doing, rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi. I promise, plug both these in, and you'll see that you get the same answer. So essentially, if you let phi go past pi, you shouldn't do that. You should go less than pi at the opposite theta value. So essentially, if you let both go 0 to 2 pi, 0 to 2 pi, you're double counting. And the other intuitive idea, too, that you could think of is that, and so we'll do a couple more examples over in this box. Basically, theta is like longitude. So if you know anything about GPS coordinates and things like that, the range of longitude is minus 180 to 180. And so essentially that's actually what theta is. And phi is latitude. I guess I should say it's like latitude. That our phi starts at the positive z-axis or the North Pole. So this is phi, and our range for phi is 0 to pi, whereas latitude is the angle from the equator. So latitude goes minus 90 degrees, or I guess you call it 90 degrees south to 90 degrees north. And so the range of latitude is actually half that of longitude. So the fact that, for example, if I have like 95 degrees north latitude, you're going past the North Pole. So 95 degrees north, you go blah, 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 blah. 90 degrees is the North Pole. 95 degrees, you've gone 5 degrees past the North Pole. You were supposed to have done that at the other longitude. So add 180 degrees to your longitude and go up 85 degrees. So 95 degrees north goes past the North Pole. that's a bad GPS coordinate. You should have gone 85 degrees at the opposite longitude. So at this point, sometimes in class, people say, well, can I do 0 to pi for theta and 0 to 2 pi for phi? Technically, that's correct, but you would have to partner that with this absolute value here, and it just gets too complicated, too annoying. So at the end of the day here, what I really want you to get out of this is that all angles is 0 to 2 pi for theta, 0 to pi for phi. So I just want to do 3 quick examples here. Let's say I want to do the z positive half of x squared plus y squared plus z squared less than or equal to 4. Let's say I want to do the z minus less than or equal to 0 half of x squared plus y squared plus z squared less than or equal to 4. And let's say I want to do the x positive half of x squared plus y squared plus z squared less than or equal to 4. So something you could see from up here is that since rho is never negative, whether z is positive or negative is determined exclusively by whether cosine phi is positive or negative. And so if you think about the behavior of cosine, z is positive corresponds to phi being acute, whereas z being negative corresponds to phi being obtuse. So remember, behavior of cosine, when is it positive, when is it negative? So positive z values, you have acute phi, and negative z values, you have obtuse phi. And so to keep z positive for this ball, I'm going to need to restrict phi to be between 0 and pi over 2. So to get that half ball, right, because phi equals pi over 2 takes me down to the xy plane, phi goes past pi over 2 is now where z is negative, below the xy plane. If I want to keep z negative, then I need to keep phi obtuse. And if instead of restricting z, I want to do something like restrict x, then you think more about how polar used to work. So to keep x positive, I'm going to restrict theta to be between minus pi over 2 and pi over 2. So again, remember, we usually think of theta between 0 and 2 pi, but when it's convenient, we are allowed to go outside of that. So instead of having to say between 3 pi over 2 and 2 pi, as well as between 0 and pi over 2, it just makes more sense to use this connected interval minus pi over 2 to pi over 2. And then I'm not restricting z, so phi is still allowed to go all the way from 0 to pi for this. So essentially, you can also think about it as, you know, the northern hemisphere, you're restricting latitudes. The southern hemisphere, you're restricting latitudes. But something like the western hemisphere or eastern hemisphere, that's when you're restricting longitude. So I know a lot of you probably don't know much about latitude and longitude, but I'd say give it a look. Check out Google. The 0 point for latitude is different. Latitude is measured from the equator, whereas our phi is measured from the North Pole, but they're conceptually the same type of idea. And so I think I just want to do one more example today. So let's say I want to calculate this, e to the x squared plus y squared plus z squared to the 3 halves, where e is a solid region inside a sphere and above a cone. So, okay, 2/3 of this is pretty standard, and it's going to be the same every time you use spherical coordinates. So I have to change x, y, and z into what they are in spherical, but I recognize that x squared plus y squared plus z squared is rho squared. So e to the rho squared to the 3 halves, and then dv is rho squared sine phi, d phi, d theta, d rho. So that dv, you have to memorize that rho squared sine phi. Recognize what x, y, and z in terms are of spherical r. That's fine. The hard part here is the bounds. So this is, I mean, this has been the story for all of our multiple integrals. Is getting the bounds is really the only thing that changes from problem to problem. The rest of it is fairly standard between each problem. Okay. So the picture that we want to think of is we have this cone. We want to stay above the cone. We want to stay inside a sphere. So our region is basically an ice cream cone type shape. That I'm inside the sphere, above the cone, and so I look something like that. And so, okay, if you start thinking about what rho starts at, what rho stops at, rho is going to start at 0 and stop at 2, of course, right? Because this sphere, remember we talked about rho equals c is a sphere of radius c. So this sphere of radius 2 becomes the equation rho equals 2. If we substitute in the fact that x squared plus y squared plus z squared is rho squared. Okay, and then theta goes all the way around, right? We're not restricting theta at all. So theta is going to go 0 to 2 pi. And then phi is going to start at 0, but it's going to stop before we get to pi over 2. It's going to stop at whatever that cone is at. And so anyway, if you rewind back towards the beginning, if you remember I mentioned, maybe I'll put this here, that r is not a spherical coordinate, but it can sometimes be good to remember. So that r is rho sine phi, that can help you with these SOHCAHTOA pictures, but also it helps when understanding these cone equations. So when I'm thinking, okay, what is this equation in spherical coordinates? Z becomes rho cosine phi, remember? So z is rho cosine phi. Square root x squared plus y squared is r, so it becomes rho sine phi. So if you play around with this equation, the cone equation becomes tan phi equals 1. And so then, therefore, remember, phi is between 0 and pi. The only solution for tan phi equals 1 in that range is that phi is pi over 4. And so that's what you get for that. So this cone is at an angle of pi over 4. So we'll practice this again tomorrow, but spheres give rho info. Cones give phi info. So that's a little bit different from what happened with cylindrical. Cylindrical, you're still thinking bottom and top z surfaces. So the z bounds in Cartesian are basically the z bounds in cylindrical. And then the x and y get jumbled together to become the r and theta bounds. So for something like this, the cone is your bottom surface, the sphere is your top surface. So your z bounds are sort of, if we were to do this, and we will do one like this tomorrow, if we were to do this in cylindrical, your z bounds would be the cone and the sphere. But when you switch into spherical, it gets kind of strange that the cone turns into the phi information and the sphere turns into the rho information. And so that's just something you're gonna have to get used to. But anyway, let's finish this off. So it looks like our bounds are all numbers. Our integrand is separable. So basically I could do 0 to 2 rho squared, simplifying my integrand, it's e to the rho cubed, d rho, and then what, 0 to 2 pi, d theta, and then 0 to pi over 4, sine phi, d phi. So what, this, if I do a substitution, u equals rho cubed, this is what, e to the rho cubed over 3 between 0 and 2 times theta between 0 and 2 pi times minus cosine phi between 0 and pi over 4. So I get what? E to the 8th over 3 times 2 pi times minus 1 over root 2 minus negative 1 is plus 1. And there we go. So I think our goal for tomorrow is, now that we've learned spherical, it'll be more important not to get confused with what's going on with cylindrical. So I'm going to show you a couple of examples. I'll show you that we can make both spherical and cylindrical work for both examples, but there's going to be a clear choice for the winner. So tomorrow, do more examples to sort of give you tips on how to decide which of these coordinate systems to use. Because on their own, they're not so bad. I know spherical is a little tricky, but the real tricky part is to not confuse details between them and to be able to decide which one to use. So that's what we'll focus on tomorrow at first. And then I'll have a little bit of an optional topic to explain where the hell these are, where rho squared sine phi, where that stuff's coming from. Essentially, what we're doing is a multivariable version of substitution that you learned back in Calc 1. And that explains where these extra factors are coming in, either on dA or on dV. So I'll show you where that stuff comes from tomorrow. But otherwise, I will see you then. It's all for today. Have a good day.